Underneath every step you take lies a masterpiece of chemical engineering. We often take the bounce in our sneakers for granted, but the journey from raw chemicals to that cloud-like comfort is a high-pressure transformation that rivals the complexity of modern aerospace materials. At the heart of this revolution is a material known as EVA, or ethylene vinyl acetate. It is a copolymer that balances the toughness of plastic with the flexibility of rubber. But on its own, it's just a solid mass. To turn it into a high-performance midsole, engineers must manipulate its molecular structure to trap millions of microscopic gas bubbles, effectively turning solid plastic into a pressurized, gas-filled matrix. This isn't just foam, it's a precision-engineered kinetic energy return system. Every millimeter of the sole is designed to compress under the weight of a human body and then snap back into its original shape in milliseconds. To achieve this, we start with raw resin pellets, appearing like small translucent diamonds. These pellets are the building blocks of the modern sneaker industry, and the secret to their performance lies in a process of controlled explosion, known as injection expansion. Let's dive deep into the factory floor to see how these tiny beads become the foundation of your favorite footwear, where temperatures reach hundreds of degrees and pressures climb to levels that would crush a car.
The process begins in the compounding stage, where the raw ethylene vinyl acetate resin is prepared. Imagine thousands of tiny, clear plastic beads, each no larger than a grain of rice. These are the primary ingredients. But pure EVA isn't enough for a marathon runner. It needs a secret recipe of additives. Workers feed these pellets into massive stainless steel hoppers, where they are blended with chemical blowing agents, cross-linking catalysts, and stabilizers. The blowing agent is the most critical component, usually a powder like azodicarbonamide. This powder remains dormant at room temperature, but it is a chemical time bomb waiting for the right moment to release nitrogen gas. Next come the pigments, concentrated dyes that give the sole its vibrant, neon, or classic white aesthetic. This dry mix is then fed into a massive extruder, a giant heated screw that grinds and melts the materials together. The friction and heat turn the mixture into a thick, viscous dough, roughly the consistency of molten honey. This molten mass is then cooled and chopped back into pellets, but these are no longer raw resin. They are now compounded pellets, preloaded with the chemical potential to expand up to 3 times their size when the heat is applied. This is where the engineering of the ride begins, balancing softness against durability and weight against energy return.
Before a single sole can be poured, engineers must create the negative space. This is the mold, a massive block of high-grade steel or aluminum alloy, CNC machined to tolerances within microns. If you look closely at the interior of the mold, you'll see thousands of tiny laser-etched textures. These aren't just for fashion, they provide structural integrity and help the foam release from the metal after the process is complete. In the how it's built world, the mold is the most expensive part of the process. A single set of molds for one sneaker size can cost tens of thousands of dollars. These molds are designed to be undersized. This is a counterintuitive part of the engineering because we aren't making the final sole yet. We are making a preform. The mold is carved to be significantly smaller than the finished sneaker, roughly 40 to 60% of the final size. This is because we are about to utilize the physics of expansion. The mold features internal channels called runners, designed to guide the molten EVA into every crevice of the heel and toe, ensuring there are no air pockets or structural weaknesses. The tool is then coated with a specialized release agent, a chemical lubricant that ensures the sticky, hot foam doesn't bond permanently to the expensive steel. It is now ready for the furnace. Now, the action moves to the injection molding machine, a hydraulic behemoth that can exert hundreds of tons of clamping force. The compounded pellets are fed into the machine's barrel, where a reciprocating screw grinds them while heaters raise the temperature to approximately 170 degrees Celsius or 340 degrees Fahrenheit. At this precise temperature, the EVA is molten, but the blowing agent hasn't fully decomposed into gas yet. It's a delicate balance. The machine then slams the mold halves together with a force of over 200 tons to prevent the pressure from blowing the mold open. Then, with a sudden burst of hydraulic power, the molten plastic is injected into the mold cavity at high velocity. This takes only a few seconds. Inside the dark, pressurized heart of the mold, the EVA fills every nook and cranny, but it's under such immense pressure that the gas produced by the blowing agent is dissolved into the liquid plastic, much like carbon dioxide is dissolved into a bottle of soda. The material is currently a dense, hot mass held captive by the steel walls. To the naked eye, nothing is happening, But on a molecular level, a massive amount of potential energy is being stored, waiting for the pressure to drop. This is the most cinematic moment in footwear manufacturing, the pop. After a few minutes of heating, the chemical cross-linking is complete and the blowing agent has fully reacted. The machine then releases the hydraulic locks and the mold pulls apart. In a fraction of a second, the atmospheric pressure drops. The dissolved nitrogen gas inside the EVA instantly seeks to escape, but it's trapped within the cross-linked polymer chains. The result? The entire midsole spontaneously expands, literally jumping out of the mold. It's like watching a marshmallow expand in a vacuum, but with violent speed. In an instant, the preform grows to its final size, increasing in volume by 200 to 300%. This is where the sneaker gets its soul. The expansion creates a closed cell structure, millions of tiny, independent bubbles that act as individual shock absorbers. If the timing is off by even 5 seconds, the foam will either be too hard or will collapse into a shriveled mess. The engineering precision required to coordinate the temperature, the chemistry, and the mechanical release is what separates a cheap flip-flop from a high-end marathon shoe. The sole is now a steaming, oversized version of itself, hot to the touch and incredibly light. Immediately after its violent expansion, the foam is unstable. Because it's still at nearly 200 degrees, the air inside the cells is hot and expanded. If left to cool naturally at room temperature, the sole would warp, shrink, or deform. To prevent this, the soles are immediately placed onto a conveyor belt and sent into a stabilization tunnel. This is a long, temperature-controlled cooling chamber, often several dozen feet long. Here, the midsoles are subjected to a specific cooling gradient, often using a combination of cool air and water mist. The goal is to set the polymer structure while the gas inside is still pressurized. This ensures the sole maintains its precise dimensions, matching the left foot to the right foot with zero tolerance for error. Think of it like tempering steel, but for foam. Engineers monitor the shrinkage rate constantly. Every batch of EVA has a slightly different expansion ratio depending on the humidity and the age of the resin, so the cooling speed must be adjusted in real time. Once the soles emerge from the other end of the tunnel, they are stable, cool, and have reached their final density, ready to take on the weight of an athlete. An engineered product is only as good as its failures. To ensure these midsoles can survive 1,000 miles of pavement, they are sent to the testing lab. Here, specialized machines put the foam through a literal torture chamber. One test involves a pneumatic piston called a durometer. It punches the foam thousands of times, mimicking the impact force of a runner's heel strike, which can be up to 3 times their body weight. Computers measure the energy return, calculating exactly how much energy the foam gives back versus how much it absorbs as heat. If the foam is too soft, it bottoms out and hurts the runner's joints. If it's too hard, it feels like walking on wooden planks. We also test for compression set, which is the foam's ability to return to its original height after being crushed. Using a precision laser scanner, engineers ensure that after 10,000 compressions, the sole hasn't lost more than a few millimeters of its loft. Finally, samples are placed in ovens and freezers to ensure the foam doesn't become brittle in the winter or turn into mush in the summer heat. Only the batches that pass these brutal trials move forward to the assembly line. The midsole is now complete, but it's still just a piece of foam. In the final stage of assembly, the bottom of the EVA is buffed and primed to receive the outsole, the durable rubber layer that provides grip. Using a process called priming, the foam is treated with a chemical wash that opens up its surface pores. A high-strength polyurethane adhesive is then applied, and the foam is bonded to the sneaker's upper, the fabric part that holds your foot. These components are placed in a hydraulic press, squeezing them together at high pressure to create a bond that is actually stronger than the materials themselves. This is the culmination of physics, chemistry, and mechanical engineering. What started as a handful of translucent plastic pellets has been melted, gassed, exploded, cooled, and crushed to become the high-performance tool on your feet. The next time you feel that bounce in your step, remember the millions of nitrogen-filled cells, the 200 tons of pressure, and the precision-engineered pop that made it all possible. This is the hidden world of sneaker engineering, where every step is supported by a marvel of modern manufacturing. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this Tech Archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.